Hey everybody, welcome to another Avalanche Developer Community Call. These are bi-weekly calls that we have with the amazing engineers from our platform team. So we give the community of developers an opportunity to sync and ask questions of our platform team and get a sense of exactly what is happening with the engineering org in general and the platform team specifically. So as usual, I'm joined by these three amazing gentlemen from the platform team, and I know they have a ton to discuss today, so I'm just going to pass the mic on over to Pog to do your thing. Thank you, gentlemen.
Cool. Yeah, good to be back. Good to see you guys again. So I think first thing we'll talk about today is going to be the changes to upcoming in Avalanche Go V10 4. 110.4. And so first off, I'm going to pass it over to Steven to talk about an awesome community contribution we got. So let me share my screen here and let me know when that's on the board. And then cool. Yeah. So Steven, take it away. I'll make this a little bit bigger.
Yeah, so we have a few things rolling into V1.10.4. So the first thing that I think we're going to go over is the proposer VM windower. So to step back a little bit and give people a bunch of context that is definitely sorely needed. The proposer VM is the virtual machine implementation that ends up actually implementing the Snowman++ basically proposer mechanism. So essentially this VM ends up dictating who can propose a block for a given chain. And the way it does this is inside of the proposer VM header, it ends up referencing a p-chain height that will be used to generate the validator set. And then based on the validator set, everyone agrees on that p-chain height because it's included in the header. They generate the validator set, and then they can determine from that some random sampling of the proposers to generate who can propose. So the way that p-chain height is actually referenced is a little bit interesting. Nodes won't actually reference their currently last accepted p-chain height necessarily because nodes will perhaps disagree on what their last accepted p-chain height is. And so we wanted to introduce some lag in this to avoid conditions where someone produces a block that references a p-chain height that a lot of the network has not actually seen or has not accepted yet. And so we introduced essentially a synchrony assumption of some number of minutes that I think is currently set to, I want to say 5 minutes. What that ends up doing is it essentially lags the p-chain height on who is proposing the validator set. So if you add a new validator, after 5 minutes, that validator will actually start being considered part of the proposer set. For Warp and for the proposer VM itself, to actually generate that validator set, you have to perform some lookback. And so we're interested on optimizing that lookback to make Warp verification as cheap and as cheap as possible. So we're looking at essentially decreasing that window from 5 minutes, which is a very lax synchrony assumption. It's not in the traditional sense a synchrony assumption for like consensus, because like consensus would say like if the synchrony assumption is broken, then like your safety or like consistency is broken. That's not really what's happening here. This is like a best effort optimization. But we're thinking of like relaxing this to something along the lines of 2 minutes. Now, in addition to this time-based window, we also have just a cap of how many diffs we will have to basically bound the amount of memory that we have to keep around here. And that's currently set to 256. And I think that the interesting, and the reason we had that bound was to just cap memory. So I think that the open question is because we are thinking about switching from using a wall clock time assumption from a wall clock time assumption to the last accepted timestamp on the P chain. If we do that change, does it still make sense to actually have the time look back at all, or should you just have the cap of the 256 blocks or 64 blocks or whatever? So the original design, as I kind of like alluded to during this conversation, was it was very much like a synchrony assumption optimization, but we could definitely switch this to just be a pure block height look back and have nothing related to for time. So I do want to first shout out that the person who opened this PR is totally unaffiliated with Ava Labs, and as far as I know, and so just want to really shout out that thanks for the open source contribution and kind of kicking this conversation off for today's call. But yeah, so
my alter ego is happy to hear.
Interested. I think Patrick, you had some thoughts here, so I don't know if you want to talk a bit, but.
No, this is also, to be perfectly clear, not my alter ego, and this is great to see someone taking a stab at an open issue that we, has a, not even one that was a good first issue particularly, and tackling it and seeing what they could do. So my fear, or kind of the thing that we're discussing right now, is whether or not this clock time is even useful, because although it's like a best effort synchrony thing, it really is only best effort for one block, and then it immediately jumps ahead again to the tip. So the simple scenario I'm thinking about is, let's say that there's no blocks for 2 minutes, or let's say 5 minutes in this case. What would happen in that case is that we would still propose basically the last accepted block, I think, in the window. And then as soon as there was another block, we would immediately just jump all the way up to the tip, instead of actually like having still some nice graceful look back on like what the window could be. And so if there was like some reason that like the propagation of that latest block was slow, or like something along those lines, it could cause some instability at tip, because some validators that are trying to validate the latest proposer VM wrapper wouldn't actually have that P-chain block yet. So for like the +1 after the gap, it'd be okay. But for the +2, I guess in that case, is where it would just hop back to like potentially some instability. So it's really a question of like, do you try to defend against the worst case here, or like the average case, which in most cases this wouldn't be a problem, and that if there was like gaps in block production, you wouldn't even end up looking back 64. Then you could, in most cases, probably look back less than 64 over a 2-minute period. So it's kind of the trade-off I'm thinking about.
So I think it's probably important to shout out kind of the origin for this. So I believe during the 1.9.12 regression, we ended up seeing both X-chain, C-chain, or all of X-chain, C-chain, and P-chain instability. Specifically, the thing at that point here is the P-chain instability, because subnets don't actually directly rely on either the X-chain or the C-chain, but they do directly rely on the P-chain. And so for the subnet validators, if some subnet validators were further ahead than others, and those others were not catching up due to P-chain instability, this is the case where we basically want to remove the usage of wall clock time to use the P-chain block header time, so that we don't just advance to the latest, because when you advance to the latest, then your subnet validator who is further ahead is going to end up proposing a block that is considered invalid, and they'll think it's valid, the other people think it's invalid, and then they start getting into this kind of like weird situation where they can't agree on block validity. So that's definitely already a bad case, but yeah, I think when you accept, so say like you have some like instability at like period, like time, A, and then after a while you see some like blocks get through. I guess your concern, Patrick, would be that at that case you still have instability, but like some blocks just manage to get through.
Usually, because in that case, usually you'd accept not just one maybe, but like a handful. And so in practice, I'm not sure it would affect anything. Now, you could overtune this and like over parameterize it to say, oh, not only is it 64 max and time based, but there's also a min look back. And so to say like, oh, if your time based is 2 minutes and it would put you back at like 30 blocks, use that. But if it puts you back at 1 block, use at least 16 diff.
Mm-hmm.
And that may be an interesting compromise, but again, that sounds like a lot of parameters, and then you have to put. So I don't know.
I will say one thing is that like if you have like a chunk of blocks and then you have another chunk of blocks, I wouldn't necessarily say that like those later chunk of blocks getting accepted are actually going to have advanced times, because they may have been proposed earlier and they were just stuck in processing. But even if they did have later times, you would still end up referencing the older block, unless you had a third group of accepted, because we keep track of the 5-minute window, but we actually point the height to the first block outside of that. So we don't keep track of like the most recent block inside the 5-minute window. It's like the first block that isn't in the 5-minute window. So like if you have like a chunk of blocks and then like 10 minutes later another chunk of blocks, if all of those blocks are like say a minute spaced internally, the first block before then is the one that's going to be referenced, which would be this earlier chunk. So yeah, I like, in my opinion, I feel like this PR is an improvement over what we have. So I think that it's reasonable. Like I don't think there's any necessarily downsides to merging this in. But yeah, there's definitely like the min idea is definitely really interesting, because then you might be able to get kind of the best of both worlds, benefits. Where you're staying, where you're staying away from this like potentially volatile tip. Because like the real assumption that we're making here, right, is that like nodes might disagree at the very tip for a short period of time during normal execution, or like for perhaps a longer period of time during like network instability. But
then you don't have to pay the full 64 look back in that case always, which seems kind of appealing there.
Yeah.
So
that could be another addition. This would be very easy to add as like just another min check in the prune here as a follow-up.
Yeah. So we'll keep discussing that, but the idea here is, we're really looking at the core of the operations to see, before we try to roll out like teleporter and some more usage of warp, that everything that powers that behind the scenes is, optimized to a level that should give stable performance. So Aaron and Steven are taking a lot of time to make sure that that is the case as best as they can. The other topic we wanted to talk about too, about what's coming in the next Avalanche Go release, is some X-chain linearization cleanup. So I'll again turn it over to Steven on that. Would it make sense for me to show just like the dev branch of like stuff that's been merged, or would you like to talk about a particular change?
So I think that really the two open PRs, which are the top two open PRs on the screen right now, actually are the ones that are probably the most interesting. So in the DAG world, we had this notion of a unique TX, which was essentially this like cache deduplicated transaction that managed various statuses and like acceptance and rejectance and things like that. And so the main complexity here was because all this stuff had to be tracked fairly rigorously in the DAG engine. We ended up needing to persist a bunch of state to disk if it was ever evicted. And so there's a lot of like complex logic on like both like caching and disk consistency, what's on disk, things like that. So this whole release has kind of been focused of saying, okay, we don't have to deal with any of that anymore. We don't have to deal with, processing status transactions being persisted to disk. We don't have to like handle rejected transactions being persisted to disk. We don't have to do any of this anymore. And so we have a various slew of PRs that will basically go through and clean up all of the and prune the X-chain database. So the On startup, you might see this kind of like committing, like pruning state log that pops up on the X chain, which should happen fully in the background. So it shouldn't impact any startup times or like time for like node to become healthy, unhealthy, things like that. But yeah, so we're going to be doing this kind of like final database cleanup. And with that database cleanup, we can finally remove the entire unique TX struct. So this is kind of the culmination of all of that work. And as part of this, we last time we dabbled too much on the X chain. We ended up introducing a pretty serious regression in the 1912 regression that we were just talking about earlier. And so to kind of like verify and like make sure that these changes are all kosher and we're all happy with it, we also introduced various state checksumming. So some people might not know this, but currently the X chain and the P chain are actually not Merkleized. They are just flat on disk. And that's really nice for my performance and disk overhead right now. So like if you actually look at the breakdown in the database on the C chain or of the Avalanche Go node, the C chain absolutely dominates because of how the Merkle tree nodes are persisted on disk. But that ends up introducing some concerns about introducing regressions where we might not delete a UTXO when we should, or things like that. So adding in these state checksums provides a really easy way for us to monitor nodes with older code and newer code and make sure that they have the exact same database content. So this is not actually tracked on disk. This is a purely in-memory checksum. And so that means that on startup, it does do a iteration to generate the current checksum of the database. So because of that, it's all hidden behind like a debug flag. So normal people probably shouldn't ever notice that this exists. But in the case that we are either debugging the client, or in the case that some database is throwing some unexpected errors, then we can enable this to kind of further dig down and figure out exactly what's going on. So I'm really excited about this state checksumming stuff. Once we end up integrating the Merkle DB into the P chain and X chain for state sync, we will definitely move away from this and just use the Merkle roots there for this. But I think that the proposer VM windower, along with all of the X chain database cleanup and the state checksumming, are kind of the major things that I'm keeping an eye out for this release. So yeah.
We were so interested at one point, or maybe I was so interested at one point in avoiding Merkleization overhead that we played around with a database concept, which we called the ludicrous database, which actually retained the ability to write directly to disk flat, but then tried to provide some state synchronization functionality using like database snapshots and like basically occasionally generated like copies of the state that could be synced and then checkmarked or checksummed as you synced it to make sure you were syncing the right thing. But that actually ended up introducing a lot of overhead on the validators that would have to produce those things. And we felt that instead having dynamic state sync on MerkleDB would be more efficient, which is why we ended up going down that path roughly 9 months or so ago. So we've been happy with it, but that is the one huge thing you end up having to give up, which is you end up having to maintain this Merkle structure on disk. But a lot of our MerkleDB stuff now allows you to tune the overhead in memory, basically. So like all the what we call intermediate nodes end up getting to like kind of stay in memory instead of being written out, which can really reduce the DB overhead, but not the hashing. So there's a slight digression there on something we thought about because we enjoyed that aspect of the XMP chain so much. So next thing we're going to go into is talking about the LiteVM and some of the stuff we've been exploring with stateless virtual machines. So last week at Avalanche, we had our company hackathon, our internal engineering hackathon, which always is a lot of fun. I sometimes am surprised by the just raw productivity of people when they don't have to do what I asked them to do. And so I think that that's a really interesting look into what's going on here. But nonetheless, I think it was really fun to work with Steven on this project. And so long story short, we were trying to push the idea of, is there a way to dramatically reduce the amount of storage that a validator would need to use to actually validate a chain? And so one of the things that you should think about when you're designing a blockchain is, what is the state replication factor? So in a traditional blockchain, like at least in Avalanche, all validators and archival nodes have all the state, all of the current state. And so as a result, they can verify blocks, they could generate transactions, they could build blocks. But it's expensive to maintain all the state, especially as state continues to get really big. Every time you add an address to state, like the amount of gigabytes or terabytes or of data you have to store to actually verify blocks and produce blocks grows. And as long as this continues to grow, the cost to actually run one of these nodes goes up. And so what data has shown is that the more complex and expensive the cost is to actually run a node, less people do it. It just gets more cumbersome, gets more expensive. Usually there's multiplicative factors of like, if the state's bigger, now I need to use fancier disks, now I need to be able to back up. You end up having all these problems that come up. And, for APIs, I guess it's one thing, right? Because they actually, people use those on a general basis. But the one thing that gets really concerning is that when the validator counts go down because the state is so expensive to maintain, because that is really the decentralization factor that most people care about, is of the people participating in consensus, how many are they? How unique are they? How distributed are they? Can I run one? And the larger the state is, the more difficult that becomes. So you can make a trade-off to say, what if we don't actually replicate the full state to everybody, and instead just have some set of nodes that anyone can run that replicate the state, but then the validators themselves only actually store a Merkle root in the block plus some window of diffs that then you can apply these proofs to. And then use that to actually verify blocks and even produce blocks, which is really cool, using transactions in the mempool. So, is it perfect? No. I think one big downside here is that, in a world where only there's partial state replication, whoever runs those API nodes really determine who can generate transactions, because you need a valid proof. And so if the APIs for a chain like this became so centralized that they went offline at some point, well, then no one could actually produce transactions anymore, which is kind of a scary reality, unless you fully resync the chain, which in the case of a stateless blockchain design, typically the validators are going to prune blocks rather than keep the full history. So they may not even be able to recreate the state. So there's some areas you need to be concerned about, but those APIs only need to store the current state, which tends to be much more manageable than endless archival. But the real goal here is to say, if we were trying to make a as decentralized as possible virtual machine, or blockchain that could be as decentralized as possible, what would it have? Well, it would probably be validators that really don't know anything other than what they immediately need to store things. Now, our estimate, probably optimistic, we're trying to win a hackathon here, but nonetheless, it's dramatically less than what the actual storage requirement would be to store the full state. Now, where this is currently implemented, so we implemented all of it. We use the Hyper Virtual Machine, or HyperSDK, because it already has this notion of state keys that must be declared for a transaction. And in this database design, or in this virtual machine design, it's really important to actually get proofs of all the stuff you're going to change. So we already got that out of the box. We didn't have to worry about it. And then we used the Merkle DB, which also had a bunch of the primitives that were needed here. And so both of these PRs are public. You can take a look at it. You can run it on your own. But what you'll quickly find, or actually, let me say that the one big challenge that we had to solve for with this is really this notion of applying changes to conflicting changes to the same root. So there's the straw man approach here, which is I have a Merkle tree. I generate some proofs of a change I'm going to make. I verify that proof. Cool. It matches the root. now I'm going to change it. I got a new root. I can generate that new root with the old root, my proof, and the change. Cool. Well, what if concurrently Steven sends a transaction that also modifies that value? Or even just modifies a value at all and has a totally different and uses the same root. Well, as soon as you process my transaction, you can no longer process Steven's transaction because the root's no longer valid to make that change, like the proof will fail. Or let's say that you somehow get around that problem and we change the same value. Well, then, his proof is going to reference a value that's no longer current. Well, can't do that. So you have to handle both of those cases to make the UX even reasonable. And our demo did, which is really fun because now you can we maintain this window of historical roots and proofs that as long as you reference a root in that window, we can validate that your proof was valid plus whatever intermediate changes occurred since then and can still apply your value using the latest change to the values that you reference, which is really, really cool because it totally gets away from this problem. So we can, we were running some demos where you're processing, hundreds, if not thousands of conflicting transactions all at once with all referring to state roots within the last, 256 blocks. So you may say, well, all this sounds really sick, especially if I want to, reduce the amount of storage the validators have to hold. Why don't you just go do it? Well, the big problem is that the proofs that are attached to the transactions right now can be pretty big. And they're also a function, at least in their naive form, of the size of the state. So on a state tree with a couple thousand accounts with a hexarray tree, you may get a proof in the range of kilobytes. And so per transaction, that could be quite a bit of overhead. Now you're making a trade-off, assuming you don't do any proof optimization, that you'd rather have much more network bandwidth than have to store state. Now, is that the right trade-off for everybody? Not sure. But we can do much more. And so there's a lot of proof optimizations that can be done, as well as relaxing proof requirements that can make this much more tenable. I'm not sure what we could get it down to, but I would assume we can make it on the order of 70 to 80% smaller than we currently have it, at least. But I think I'm most excited about the relaxed proof requirements. And then I'll turn it over to Steven to add anything to this. But the idea is, if your transaction is referencing values that have been already proved in the last window, you don't actually need to update a proof for that value because the validators already know what the value is and what changes were there, which is kind of nuts, right? Because then if there's some hotspot or some account is always modifying something, it actually now just looks like a normal account entirely, and there's no overhead, and it's stateless. So if you have a large enough window, and you have a large enough, or you have a power law of values basically that are touched, on the average case for many people, it may only include proving one value that's unique for what they're doing, or no values at all if you're a power user. So it may end up, we may be able to get to an interesting middle ground here outside of any proof compression or proof changes that could unlock, actually a solution here that may be manageable. So, but yeah, Steven, I don't know if there's anything else you wanted to add that he did most of the hard work.
There's so much more I want to add. But so one interesting thing is that the Merkle tree structure is very critical for this design. So actually, so as an example, Ethereum's hexarray Merkle tree wouldn't really work in this case because there's some unnecessary quote unquote hashing that can happen because of the way that they handle extension nodes. And so as part of the design for MerkleDB, we really aggressively tried to make sure that we minimize the number of hashes that were being performed during modifications, because the two bottlenecks typically in Merkle trees is the disk overhead and the hashing. So by minimizing the number of hashes that you need to actually perform, luckily for us, we also ended up generating a tree structure that didn't necessarily need reconfigurations of hash nodes when deleting tri-E nodes, which means that you can kind of, or you don't necessarily need to have additional data if you have two different like deletes that come in that end up compressing a new node. So this is not generally true for Merkle trees. So if you're trying to do this at home on your own Merkle tree, watch out because the structure definitely gets pretty complicated. But yeah, the proof compression idea, essentially, and this is really more just because we did this as a hackathon than anything else, but currently our proofs have just a ton of useless extra data. Ideally, you would want to have a proof tree when you're performing inclusion and exclusion proofs over multiple key value pairs. But the way that we currently do it is we have like independent inclusion exclusion proofs for different values, which means like, you're going to have like the root stored in your proofs n times for like n key value pairs rather than just the once, because the root is always the same if you're proving against the same root, and things like that. So there's a lot of like very easy overhead to remove. But yeah, I think, there's also some interesting talk. I don't know if we want to do an aside into ZK world with this as well, but there was an interesting discussion that was posted on the HyperSDK around ZK proofs and using basically ZK instead of using Merkle stuff. And I think that the nicety here is that you get this world where you have essentially your API nodes have the full state. And so as long as you can sync off of any of these API nodes, so you basically just have to have one correct API node that will serve you data in order to like join the system. And that API node is not actually the node determining the next step. So in the ZK rollup world, you have this kind of like sequencer that has all of the data, generates a new thing, and like advances it forward, or say like some threshold of these. But the actual committed state in the blockchain is just the zero knowledge proof of that transfer. So you end up needing to post essentially the Merkle proofs here as data availability problems. And so like people then maintain these, and you assume that you have someone with the data that you can sync off of to reconstitute the same tree. The thing that's nice here is that that's kind of included already in the whole chain. So you have all of the diffs in the chain, and you're basically assuming that people can keep up to date with the chain. And if they wanted to join as a new person, then they would join based off of at least one correct peer that is running an API node, essentially. And so I think if we start introducing like ZK into this, it starts transferring into more of a ZK rollup thing, at which point you run into problems around like actual data availability, whereas here you don't necessarily have to worry about that too much because all of the proofs are already on chain. Of course, in the ZK world, you might be able to like shard the data more, whereas in this case, we're kind of like in a like the current suggestion for like 4844, I think that's the EIP for dank sharding, proto dank sharding or whatever, where like all nodes still have the data. That's kind of like what this would look like because all nodes have the Merkle diffs. But yeah, it's pretty interesting and how it kind of like can avoid a lot of both the ZK complexity and also like the data availability complexity here. Yeah, I think that's kind of all I wanted to say. It'll be interesting to see where this goes. I think I've been talking about stateless VMs for literally years. I was ranting to Aaron about it when we were at Cornell in college, so so he can attest this. I've been talking about it for a while, I think. Yeah, happy to see us finally working on some stuff here.
It's a good topic when GitHub says the original comment is in Spanish on the discussion, and it's definitely not. So I think the comment that this discussion is linked, if anyone has anyone to chime in on it or discuss it. We're trying to use GitHub discussions more to have some of these conversations rather than getting lost in Discord or Telegram or something like that. So if you have any thoughts or want to work on it, all the PRs are listed there, and everything that we want to do to get it ready for production is also listed there. So for this, we really think of it more as like an option for the HyperSDK based on your use case, rather than something that's strictly required or something that we have to do with it. We'll come back to this kind of in the questions. I see someone asked an interesting one in the chat. So the other thing I wanted to feature was a new tool that we're going to start that's actually public right now that we haven't marketed yet. And so we just released a open source implementation of a mnemonic Shamir secret sharing tool. So this is a total change up for what I was just talking about, the HyperSDK. But it's cool, and I want to feature it in here for people that are stopping by the dev community call. So this is a common thing that if you have a core, like a wallet, that may be something that's useful to you, which is, you have your 24-word, secret. Well, oftentimes when you want to back it up, you don't want to back up that specific thing somewhere. Maybe you do, but if someone takes that thing, your money's gone. What if you could just put in your secret into this tool, and it would spit out N other 24-word phrases, and if you bring together any T of those phrases, you can reassemble the original secret. And so that's what this tool does. So let's say you wanted to take your secret, split it up into 5 chunks. If 3 of the 5 chunks are combined, it can produce your secret, and then you store those 5 chunks in totally different places. And so this tool allows you to do that. So it's fun to play around with, especially for like simple tools, simple seeds. Like we have a few examples here you can play around with and make sure it works and everything like that. But it's a fun tool. Obviously, it assumes you're using this on very secure hardware. It's tested but not audited yet. So use it at your own risk. But it's fun to play around with, and a cool tool that we've been experimenting with internally and thought it could be useful to the community. So we decided to open source that. So feel free to take a look at that. So the next thing we were going to go to, and we're flying through time here, was to actually talk about some of the work we've been doing on deferred validation. And so one big topic, see you've unmuted, Steven, is there something you wanted to say?
I was just going to comment that we should, going forward, we should probably think about bringing in the people that work. So I think for the Shamir secret sharing stuff, I think it would have been great to have Michael hop on here and talk about it, because I love Shamir secret sharing, and I bet he could have some interesting comments. So maybe for the next call, we could see if he could join and talk about it. But yeah.
Yeah, I think, it's a good point. I had nothing to do with the creation of this. I don't think Steven did either. So I think the people to shout out to in that case, I found this really cool tool on GitHub where you can combine all the authors into a single commit, would be Michael, Arnold, Marcelo, and then Sasha all played a part in getting this tool up. So but all in C++ too. Shocker, not in Rust, not in Go. So if you want to take a look at that, check it out. So so the next thing we wanted to talk about was the deferred verification conversation, which is something that we've also been experimenting with. So long story short, I've been kind of in a cave somewhere trying to make the HyperSDK as fast as possible. And with the deep support of everyone else on the platform team, but mostly me like hooking it up to random dev nets and seeing how fast I can make it go, and then complaining when certain parts of it aren't fast enough, and then we'll figure out what those parts are and make it faster. But at some point, the HyperSDK relied on the traditional verification model. And so that idea basically is when you get a block over the wire, you verify that block. And then once you've verified that block, you can start voting on it in consensus. And then once consensus accepts, or rejects, you accept or reject that block and commit it to state. The problem is that when you get to really high throughput, that verification requirement, even if you get creative with it, ends up being the bottleneck most of the time. So like in that verification step, you may execute transactions, you may modify state, you may generate state roots, You may verify signatures. There's a lot going on there. And if that's the required to like build really the next block or verify it, it ends up slowing down the whole process, no matter how much compute you throw at the problem, unless you do some fancy like sequencing of it in some way. And so, you know, while I toiled to try and make that as efficient as possible, which I think it ended up getting pretty efficient, nonetheless, it was still non-zero. And as a result, I was not able to actually utilize the full capacity of the machines I was running it on. Although it was hitting, you know, 50,000 plus TPS on these dev nets, it was not fully exhausting the CPU of the nodes, which is clearly there's something wrong. Like if you're trying to like max out a computer, but you can't get it to max CPU, like clearly you have something to learn about programming to get it to that level. And so I'm still learning what those things are, but nonetheless, it was in the verification loop. And so the idea is, can we do anything to really change the data that's actually part of consensus such that you don't need to do nearly as much verification on it? So maybe you don't actually have to generate state routine. Maybe you don't even have to execute the transactions. And so that is what this whole deep dive was on, is what if we can just agree safely somehow on the execution inputs, and then because the blockchain is deterministic, we are more or less implicitly agreeing on the execution results. And then we can actually do all of that execution after we've even accepted the block, where we have non-bottlenecked compute time, or like non-hot path compute time, where we can generate the root, make all the changes to state, and do everything there. And so what that allows you to do then is it almost like turns the consensus part really into like a data agreement problem, which is, let's stuff as many transactions as we can in, as long as they have a signature and can pay fees. We don't really care what they actually end up doing, but like, let's put them in. And then if you can pay the fees and the signature is valid, like, frankly, that's all I need to know to put it in consensus. And so then once it's in consensus and we actually agree on it, then I'll actually deduct your balances. And so to make that work, we just have to maintain kind of this like really fast in-memory view of what balances may be. And we need to separate the balance between the executable balance and then the data balance, because a lot of times the problem with the executable balance is you can have an interactive or like a really complex smart contract interaction that drains that balance. And then now, you know, what looked like you had balance 5 blocks ago, after that latest block, you now have nothing, and now you didn't pay anything. So the only weird semantic thing is that you have to separate that balance kind of. And so I'm still thinking about the UX of what that'll look like, but it almost becomes like your data balance versus your execute balance, and trying to make sure that it makes sense. But the big, really cool thing that this ends up allowing is that in the verification, deferred verification part, you can start to do some like very large batch work. So like maybe you don't need to, like you can process a number of changes all at once, maybe across a number of blocks rather than strictly keeping to the block boundary, which is really cool. Or you can have much slower running verification work that if you had to verify every time you got a block inbound, could be a trivial DOS. You could wait for actually the acceptance barrier to even kick off that work. So those are two really cool benefits of of having this structure. I think the complexity is that it makes some of the state sync and some of the UX potentially more complicated. But as we've talked about the HyperSDK a number of times, like the goal here is not to just increase performance a bit; it's to increase performance a lot. And if we have to make some trade-offs to make that happen, we're willing to entertain those ideas. And so in this case, we did. So I know, Stephen, you had some ideas on the deferred verification story. And so I'm not sure if there's anything you want to add, or Aaron, I know you thought about this too.
If Aaron, you want to jump in, I've talked quite a bit. I don't know if you want
to. I'll let you go first.
Okay, all right.
I think Patrick did a lot.
Yeah. Yeah. No, I've definitely heard of people doing this, but I either didn't look in enough, or they weren't really kind of performing the early verification. So I've definitely heard of people just kind of like agreeing on data and then having, a a virtual machine post facto, iterating over your agreed upon data and just kind of like kicking out invalid stuff. But the really tricky and kind of fun part here is making it so that the stuff that you agree on is valid. You just don't know what it actually iterates to or evaluates to. So that's definitely kind of the interesting part. I've definitely thought a lot about the UX specifically with if you want to support transactions that have like something similar to a Ethereum gas limit, where you're only paying for the gas you use, but you bound how much you will use. That's a pretty interesting problem space, because if you don't actually execute it, you don't necessarily know how long it's going to run. So you don't necessarily know how many computational units you've included in the block up to that point. So a simple way is to just not do any gas refunds and say, well, you set your limit, that's what it is. But that can end up being pretty problematic for interacting with things that have, like a DeFi slippage limiter, where like, you submit a transaction and basically you can either market buy or you might just burn all of your gas and do nothing. So that's kind of the hard area right now. Like you can definitely do balance tracking where you deduct the limit from your data account and you provide refunds into the computation account, which could be really interesting to avoid some of this problem. But then there's kind of a concern on, well, how are you correctly limiting how much compute goes into the end block, and making sure that there isn't a DOS where someone submits a transaction that takes up the full limit, but then immediately returns. And so you basically have like a no-op block that is getting fully refunded. So there's definitely some interesting questions here that we're still thinking about. But
yeah, one thing maybe we could talk about is we talked a bit about that thing we discussed last time with breaking it up into sort of discrete units of time, where you start with an initial balance of, let's say, 100 units in your sort of data payment account. And then you break it up into like, I will allow you to spend this amount over the course of, let's say, 10 blocks or 100 seconds, whatever it may be. And then you sort of track and make sure you don't go below that. And then during that time, there's only a certain amount that you could actually try to go over. And if you do, then there's a cap on how much gas or how much data you could jam in there that you would end up not paying for. So you sort of like cap off your worst case. And then when you go to the next unit of time, you start tracking again, fresh, exactly how much data per account is going to be paid for and ordered. So you sort of like limit the total DOS that could occur if you do end up having gas that couldn't be paid for. This is something Steven and I talked with someone from a university a few weeks ago, and he told us this was something that a bunch of interesting people at the XDM folks were doing, and we didn't have the full details on it. But now that we've sort of talked it through a bit more, maybe we could talk a bit about the compare and contrast between this model of like capping what the worst case is of how much data you could be forced to order without actually getting paid for it, versus tracking the payment for data ordering versus actual execution. They're two very different, interesting models. I don't know what you guys think.
So I mean, this is what I wanted to do originally, actually, and then Steven was like, "It's not a good idea, not a good idea." And the problem is that you can Sybil it pretty easily with like infinite accounts, and the problem ends up being actually not to think about the block quality as a whole, but the point Steven brought up, which I think is really important, is actually how you avoid strictly the proposer getting DOSed in the mempool, so they can actually choose what to put in. Like, and to me, the takeaway I had from that is like, if you have a mechanism that doesn't let a proposer that wants to act the right way, something's broken probably. And I think that's what I kind of latched onto, is something that I was like, maybe there's a better way to do this that doesn't just involve giving everyone like a data allocation, assuming that half the transactions in a block could be valid, and saying, well, if a transaction is valid, the proposer gets a fee refund and such. Like, now that's good enough. Well, great, but the problem is that the proposer can't determine or optimize it all. Like if there's no tools to determine what fee that I could get, like it's kind of for naught. Like if you can't take advantage of an incentive, is it an incentive? And
well, I guess the
so
super obvious thing to calculate is to actually just execute it, but we're assuming that that's going to be
well. So the
slow
whole
and tail
point is
behind.
like to say yes, you could like you could. It incentivizes someone to build like some hyper optimized executor that could execute at the speed of the data, but now we're getting away from the point entirely, which is like we're trying to avoid that. My response to that would be say, yeah, I think there's two approaches. Where I've landed is like, let's try and make the one that's accessible to the operators. It doesn't require a bunch of out of the box, like proposer builder separation to make money.
Could you talk about
to run a normal network?
Could you talk about where it is that it ends up creating a DOS vector in the mempool or block builder? I don't actually know.
So let's say that like you give an allocation per account for like data that can be run. Well, what stops me from like giving a little funds to 10,000 accounts and then having each send one invalid transaction? Like, unless you limit the group as a whole, well, then now you're also destroying the quality of service for people that are legit. So to me, it turned into like a rabbit hole of a problem. And before I took one more step down to that rabbit hole, I was like, I'll talk to Steve and see if if he even is interested in entertaining the rabbit hole and whether or not I should spend time on it. And I think we had a productive conversation of like, I don't think this is the right approach if the UX isn't too bad to avoid it, which I ended up agreeing with.
So to avoid it, we go back from tracking like these in units of time where everybody has some amount that they could potentially go over, which creates the Sybil vector. And then we switch to actually tracking it exactly, and there's no discrete units of time or anything like that.
Yeah, and the way that you do that is you separate the balance account in a way that allows you to do that. Now, that's the pain point, and I'm still figuring out exactly what that means, because let's say that you want to send someone value. Well, if you don't send that value first to their fee account, kind of stuck, because now we're just going to say anything that they submit is invalid, even though they have money. So, there are UX things that we're still working through on that perspective, but I think that they're surmountable. And so we'll see where we end up with it, but that would allow you to more or less just maintain like in-memory balances of everybody, which are wicked fast to look up. And then again, because of my unintentional foresight, the auth module on all of the HyperSDK actions actually requires you to specify a single fee paying address, no matter how complex your actual thing is. So it's fully compatible with this requirement with no modifications to the actual existing like authentication interface.
Prolific, dude.
Yeah. Another thing Steven made me do, which was like, I was like, oh, it'll be fine. It was just simple auth. No. It had to be auth modules, account abstraction. But I made this concession because otherwise fee tracking becomes really hard. So it works with everything. We just need to like implement all the in-memory diff tracking kind of part. And then I should have a full POC of this whole thing in action, and we can see how fast it actually is.
Yeah, I think we should be able to get everything running, assuming no computation refunds. And I think
one-way fee account.
Well, it's not just the one-way fee account. What I mean by that is like in the data that you're agreeing on, you specify the limit of computation. Is like,
which is already how it works.
Yeah. So, but like without a refund, I don't know.
So actually, this is interesting. So I was actually thinking about it also differently, which is you could also think about it as what you're paying for is not that fee, but your bytes you're putting into the chain. But I think using the compute fee may make more sense from that perspective.
Yeah,
if you're trying to limit the amount of units per block rather than the amount of bytes per block still.
Yeah, I just worry that we run into a DOS on like we've agreed on these bytes, and then like you have some like huge amount of like compute inside of that payload, But yeah.
And that transaction could still fail on the inner side, but you paid the bytes, right? And that's probably not good enough. Yeah. Yeah. So another one that has a discussion you can chime in on if you want to chat about how this could go. But yeah, we hope with this change and some of like the nano block architecture I already talked about, that we could really achieve some interesting performance results. And then the big benefit here is that none of this requires any changes so far to the VM. This is all happening behind the scenes, which is pretty cool. As a VM builder, you can just kind of like build your VM, implement the interface, and then we maintain those invariants, but behind the scenes may do wild shit to get you to that, to hyper performance there. So we are getting kind of close to the close here. We have a number of other topics we did want to cover, but as usual, we're out of time. So we will go to now a few questions that people had asked. The first one we'll take actually is from TCrypt in the comments, Tyler Smith. So it's cool that you've been working on statelessness. It's been discussed for years with no progress. Are you considering making the Exchange use this new VM eventually if it pans out?
Good question. So I will say beforehand that I timed this really well, and my laptop is currently on 3% battery right when we were supposed to end this call. So if I just drop, that's what happened. But I hadn't really thought about integrating this into the Exchange. I would probably be pretty interested. It would definitely be a very big list, though. Yeah.
So there's a list of items actually on this point in particular of items remaining for productionizing the statelessness proof mechanism, which we kind of enumerated a short list of things that we'd like to do before we actually try to roll it out in prod. And so take a look at this as like some stuff that we think would be required, but. Yeah, I think it's something where we're thinking between those two lines right now of how we'd actually employ it and where we'd employ it, because it ends up bringing up that problem of like, how do you view state replication and which chains should require full state replication versus not? Like, should the primary network, should just some subnets not require it? But I think the first step is just making like a super performant version of this, and then we can back into where it may make sense to, as a community, kind of put something like this. So yeah, good question. Another question I had here, and hopefully Steve doesn't drop off because this is something that he may chime in a lot in. So Celsic, I think is how you pronounce it, asked a question: slashing advantages and disadvantages on blockchain networks, and why Avalanche prefers a light slashing policy compared to other networks.
I think that my stance on slashing has always been that I don't want people to be worried about losing money. I would say that for the common use case, like I'm taking a step back, which is like the common like person, not a crypto user. Someone that is looking at all of the various like hacks and like various DeFi protocols and stuff, like, you can play around with this like world, and then if you have one misstep, you just get absolutely wrecked. You lose all your money. That is a very bad UX, and I think that that's a major detractor for why people are actually joining into the system. And it's very similar, or there's a very similar analogy between that, like DeFi users and like network validator operators. So I definitely don't want people to feel like well-intentioned people. I don't want well-intentioned people to feel like they are putting themselves at a large amount of risk by validating a network. And so because of the various slashing events that have happened due to malicious behavior, or I tried to, and sometimes it's actually the exact opposite of they're trying to be the most virtuous person possible, where they have like a backup node in like Cosmos to like make sure that if their one node goes down, they can immediately like swap in their new node to like be the best person. And all of a sudden they like accidentally run with like a dual cert and like dual sign a block, and then they get slashed for it, even though they were like doing their absolute best. So Also, with slashing, I think that you run into a very scary world of if you have a client bug, especially if you have a diverse set of clients, where some client is going to have a bug that causes a slashable event, and then you always say like, oh, client diversity is like so good. Well, client diversity isn't going to happen if you have a minority client user base get slashed, because that user base is going to evaporate immediately and go to a majority client. So like, I think that there's a lot of downsides to slashing, that you have people in like the theory land being like, slashing is good because it gives the network a higher ability to punish bad actors. You get to dip in and to the principal, and so you have better economic disincentives. But you also have a lot of these practical cons to slashing, which are not theoretical issues, but are real world problems. And so that's kind of my spiel against slashing. There's also other practical reasons why Avalanche isn't necessarily set up for slashing. With like subsampling, it's not necessarily easy to have proofs of equivocation using Snow consensus because there's not this all-to-all communication. You could definitely slash on like equivocating block proposers with Snowman++ and things like that. Or also like equivocating, say like warp messages, or like if we introduced client certificates and things like that. So there are places where slashing could fit in, but for the general consensus mechanism, it really doesn't fit in that easily without like a lot of overhead. So there's kind of like, I want to say like ideological reasons that I think slashing is maybe not very good. But then there's also like the real world, like Snow consensus practical reasons. So, yeah.
The other thing to note is that there is still a disincentive for not participating. There Stephen goes. There's still there is a disincentive for not participating still, which is that you just do not receive a reward if you do not participate. And so that still amounts to more or less like a 8% loss of rewards right now. So it is still like not a free thing, but it's more of like a loss of upside rather than penalty of downside. But we've been talking about this a lot lately because we're going to introduce something called unprovable penalties, which I'm going to kind of write a thread about in a bit, that allows a virtual machine to penalize the uptime of certain peers that do something that the virtual machine thinks they shouldn't. So in the case of warp messaging, for example, if I'm trying to create a warp signature and then your validator is just saying like, nope, don't have it, and you're part of the set and it's a valid transaction, well, I should penalize you for that because it's expected of the virtual machine that you can produce that signature if you've registered a BLS key. So things like that, where it could be really useful, or in like a data availability subnet where like I can prove that you gave me the data, but I can't prove that you didn't give me the data. And so it also helps with that case, which is if you're trying to like, kind of run like a decentralized CDN or something like that, or like a decentralized file store system, and people are not responding to you, you can't prove that. But if enough people witness that, then you can like have an unprovable proof by decrementing their uptime, which is kind of a cool concept that we'll be able to employ here. I know there's 2 more questions here. We'll save those for next time. I think we're kind of running out of time here. So I'll bring Gabriel back on to wrap us up here. Oh, there's Stephen. He's alive still.
Yeah, Stephen is fine.
There's my camera. Can you guys hear me okay?
Yep.
Okay. All right. Thank you guys so much. Another very informative session. As I mentioned before, these calls are bi-weekly. So we will be back in 2 weeks. So if you didn't get your question in today, or if something came to your mind while they were discussing, feel free to save that question for next time. So I'm just going to pass the mic around one last time for final thoughts. Aaron.
Thanks, guys, for coming again. Really interesting to go deeper into some of the more technical things. I think we're really starting to hit our stride with finding, what we really enjoy talking about. So I hope everybody enjoys that too. Thanks for having me.
Yeah.
Awesome. Patrick, go for it.
My takeaway would be like, we have talked a lot about stuff that we're curious about. If you'd like to propose a discussion topic and we like kind of compile a long list of those, we can spend the whole time chatting about those with people that come on. So If there is anything, you want to discuss, there's a form linked on some tweets somewhere or in my comments. Feel free to, throw some ideas there, and we'd be happy to debate it with just amongst us, or even with you if you want to come up and kind of chat about it. So, yeah.
Awesome. Thank you, gentlemen. I am Gabriel Cardona. You can find me on Twitter at CG Cardona. That's CGCARDONA. We also have an Avalanche Developers, as one word, Avalanche Developers Twitter account that you can reach out to and also follow to get the latest and greatest from the engineering team. And then also, pardon me, I want to mention there is an Avalanche Builders Telegram chat. And this is for the Super Alpha. This is where we're connecting with people who are actively building on the Avalanche network. If that's something that sounds interesting to you, please reach out to Luigi or somebody from the Developer Relations Squad, and we will see about getting you added to the Telegram chat. So we will be back. We will be back in 2 weeks, and we look forward to seeing everybody then. Thank you again, gentlemen. Cheers.
Thanks everybody.
Bye.